Hello and welcome. I hope everyone's having a good Spark Summit so far. I'm Josh Gilner with Apple's detection engineering team. In this session, we'll be taking a look at threat detection using Spark and Databricks with a specific focus on some of the neat tricks we've developed to overcome the challenges of scale. So let's start with who my team is and what we do. At a high level, Apple's detection engineering team consumes the telemetry that's emitted by systems across our corporate infrastructure. Everything from host level log data to network sockets to application events. Our job is to sift through the data for patterns which could indicate malicious activity like malware or hackers on the network. It can be pretty challenging because we're looking for people who are trying to hide their behavior and blend in with normal usage in the data. But that's what makes it fun. To do this, we use many different technologies, some off the shelf and some custom developed. These are the ones that we'll be focusing in on a little bit more in this talk. Before we dive into details, it's important to level set on some of the terminology we'll use. We'll start by looking at what we call a detection, or the most basic unit of code for the building blocks of our monitoring program. A detection is a piece of business logic that inputs some data, applies any arbitrary number of transformations or pattern matching or statistics, and then it spits out a security alert. We encapsulate these as Scala classes, where generally there's a one class to one notebook to one Databricks job relationship. Each of these can do pretty vastly different things, but they all generally conform to the same paradigm with the same components. After one of these jobs has found something potentially malicious, the alert is fed into an orchestration system. We have a team of security analysts continuously triaging the alerts to figure out if they're a real security issue or just something that looks suspicious but ultimately poses no risk. After the analysts finish analyzing, the orchestration system has hooks into internal systems that can be used to respond and contain a security issue. Things like locking accounts or kicking machines off the network. In certain cases, the orchestration system may already have enough information to contain an issue without a human being involved. And we'll take a look at that a bit more later. Now that we have an understanding of the general flow of those detections, let's take a look at some of the problems that came up as we continued writing more and more of these detection jobs. The first was an unjustifiable degree of overhead in deploying new detections. Most of the code for basic IO and common transformations was exactly the same, just re-implemented across many notebooks. And each of these jobs needed a corresponding test, with people manually preserving sample files and writing Scala tests. This meant that we were unsustainably coming up with cool new ideas faster than we could churn them out. Other problems started to surface only after we had already deployed a bunch of these jobs. Changing the behavior of all or a subset of the detections required a massive refactor across all these different notebooks, even if the feature you wanted was comparatively minor. Each job needs some degree of ongoing maintenance and performance tuning, which can get pretty tedious with all of these disparate configs and logic. There are some common patterns people tend to use in these detections. Things like enrichments or statistical baseline that compare the novelty of current activity against historical data. But what we saw was that without any primitives at their disposal, everyone had their own special way of solving the same problems. And when we needed to update or fix them, we would have to figure out each implementation. To really take our detections to the next level, we needed to formalize how they're written and make better use of our limited human capacity. So we started a journey to find a solution to these. We talked with a lot of industry partners and looked at some third party products, but we're really unsatisfied because we couldn't find anything that suited our needs. So we spent a few months and arrived at a major breakthrough, an entirely new SDK for security detection called Detection Kit. This framework dramatically reduces the complexity of writing new detections and helps us react faster by improving the alert quality and automating the investigations. There are way too many features to dive into here, but I'll highlight a few of them. Let's start with inputs since they're the first step in any detection. The data sets loaded by these jobs need to change situationally. In production, they'll want a Hive table name, and in the context of a functional test, they'll want the path of a preserved sample file in DBFS. This means that the options of spark.read have to be externalized and passed in from the outside of the class through config. But we took it a step further, building a switch between spark.read and spark.readstream with an externally provided partition filter. It allows us to change from a streaming to a batch detection on demand without changing the class itself. In most cases, a detection acts like a bucket containing different pieces of logic which all look for different aspects of the same general high level attack. In terms of the code structure, we like to say that there are multiple alerts in a detection, where each alert is described as a Spark data frame resulting from some transform on the input. The detection class creates and exposes a key value map of all the alert names to their respective data frames, which can be consumed either by other detections or the post processing methods that are applied before an event is sent for the analyst to review. Much like we externalize control of detection input, emitters do the same thing but for output sinks. In production, we send alerts to AWS Kinesis, but in other situations may call for writing a disk or an in-memory table. An emitter wraps all of these output parameters like a target Kinesis queue, file paths, or stream options. Much like inputs, emitters are also provided in config, so you can easily change the output behavior of the detection without modifying the class. There are a lot of small details required by these jobs that are pretty annoying to provide, like the streaming checkpoint paths or the scheduler pools. We found that most of them can be inferred by convention using parameters that are already in the config object, with optional overrides only if people want to specify them manually. This minimizes the amount of required fields and simplifies our config structure. A detection can contain multiple related but independent alerts, and most of the time, you'd want them to be configured in the same way. Things like using the same emitter or inferring the parameters by the same convention. By default, they'll inherit the configuration of the parent detection, but remain individually configurable should you want granular control of them. We can think of a detection as a sequence of data frame transformations. The first transform in this sequence, or what we like to call the preprocessor, is a method that's supplied in config to be applied before the core detection logic. This is an ideal place to inject certain types of operations like partition filters that'll determine how much of the input data will be processed, or the pushdown predicate on a stream to tell it where to start. After all the data has been processed and we've yielded a set of suspicious events, there may be some additional enrichments to apply right before they're emitted, many of which are common amongst multiple jobs. To make this easier, we've broken out some common transformation into reusable modules, which are defined in a mutable Scala list and applied sequentially at the end of the detection. Finally, there may be certain types of operations which are not natively supported by the structured streaming APIs. For those, we can specify a transform function to be applied within a for each batch. And we'll talk about a specific example of this in more detail later. Detections are inherently imperfect. They're designed to look for anomalies in datasets that are sometimes chock full of these weird little edge cases and idiosyncrasies that can change over time and are really difficult to predict even if you have all the historical data in the world. Actual humans review these events, so the signal to noise ratio is really important. And we continuously tweak the detections using these analyst suggestions. But doing them one by one takes a lot of time. And while they're being worked on, we don't have any cycles to write new detections. When analysts triage alerts, they label them as either false positive if it found something that wasn't a real security issue, or a true positive if it's actually malicious. This feedback is memorialized in a Delta table where we've incorporated it back into the detection pipeline. Rather than us manually tweaking each of these detections, the system learns from the analyst consensus and automatically adjusts the future behavior. In this way, the bulk of this day-to-day tuning is self-service, and we saw about a 70% reduction in the total alert volume when we deployed this, which was pretty nice. In some cases that are difficult for that automation to figure out, we may still have to do some degree of manual tuning. Each round of this tuning adds an exclusion to the detection logic until inevitably it looks like the top right hand side there. You end up with these really ugly addendums that are almost as big as the detection logic itself. Not this thing, not that thing, over and over and over again. To solve this, we built a new mechanism which breaks out a list of SQL expressions that are applied against all of alert output in the for each batch transform at the very end. It allows us to be as complex as we want in the exclusion logic while still keeping the detection classes pretty clean. And because they're integrated into our functional tests, we can ensure that overly selective or malformed SQL expressions are caught before they impact the production jobs. Although the matching events to these expressions are excluded from what analysts see, we don't just want to drop them on the floor. All of the excluded events are written into their own table so we can continuously monitor the number of records that are excluded by each expression individually. Let's take a look at what happens during alert triage. Typically, there isn't enough information inside the alert on its own to render a verdict. And they'll want to run some ad hoc queries in a notebook to gather some substantiating data. They'll need to take some parameters from the alert payload, create a notebook and fill it out, and then sit around and wait for these queries to finish. A lot of the information they're looking for doesn't really change all that much from investigation to investigation. Things like what happened immediately before and after the alert, and what does this machine or this account typically do? To help with this, we've used the Databricks Workspace API to templatize and automate the execution of investigation notebooks. Each detection has a corresponding template notebook in a specific directory, which the orchestration system clones and populates with information from the alert. And because many of the queries are the same between similar categories of detection, we can modularize the templates and reuse components with the %run magic command in notebooks. This functionality arms our analysts with the information they'll need to make faster decisions, and it also abstracts the complexity of some neat things that people wouldn't usually do manually. On all the detections surrounding a suspicious process execution, some custom D3 will render an interactive process tree that'll let you trace the PID lineage and its relationships. In this example, there was an interactive reverse shell following exploitation of a Java web server process, something that would have been pretty difficult to figure this out if you're just looking at records in a table. We've also taken some queries that would be executed in a template notebook and had the orchestration system run them via ODBC. Rather than a human interpreting the results in a notebook, the machine can evaluate the current activity that's happening against the historical baseline it collects and render a verdict. If it's confident enough in the verdict, it can automatically contain the issue without a human even being involved. So you'd end up with these detections that test well, but don't necessarily work in the real world. And since fully structured binary formats like Delta don't play that well with revision control, we had to use semi-structured formats like JSON and worry about codifying the schemas into our test suite. So we wrote a test generation library that wraps Scala tests, and we can run them right inside notebooks. Using only the information in the config object, it'll create an assertion for each alert and infer the paths of the hits and samples by convention. So the only thing you need to worry about as the author of a test is writing your samples and hits to the right place. With this, we've seen a dramatic 85% reduction in the amount of code it takes to write a basic test for a detection. But we took it a step further and integrated the notebook-based test into our CI. It'll clone notebooks from the PR into a specific directory and execute them on a real cluster that returns a JSON object summarizing the test results via dbutils. Our CI system gathers these results and will pass or fail the build based on what happened remotely in the Databricks instance. It also frees us up to write detections that do things which wouldn't normally work in an IDE, like %run imports of other notebook components. Once these tests pass and the production notebook lands in Databricks, we still had to manually create and configure jobs that would execute the notebook tasks. Each one might need a specific cron expression or want to run on a certain cluster, and all these details were typed in and maintained by hand. At a certain point, we had way too many of these detection jobs to continue managing them with the Databricks UI, and no real way of making bulk changes like moving a bunch of jobs between clusters. But Databricks recently announced a really nifty beta feature called Stacks. It's a dream come true for anyone who's looking to build a job CI system because it removes most of the complexity from maintaining inventory and state across the different Databricks APIs. You can package a job and all of the resources it needs, like notebooks or DBFS files, into a tiny little config stanza, and it gets deployed all at once as a package. So we built a fully featured job CI on top of this Stacks CLI. All of our notebooks, files, and job parameters can now exist in Git, with CI doing the heavy lifting for job deployment. We lint the Stacks config objects and then pass them into the CLI, which creates or overwrites any of the resources as necessary. But for jobs specifically, there were some important finishing touches which aren't currently covered by Stacks. We augmented the CLI with a couple helper scripts that'll kickstart newly created jobs, or if a job or the underlying resources has changed, it'll restart them to accept the new config. Job CI was the last piece of the puzzle for us in automating every piece of the deployment, testing, and the management of the detections from end to end. So far, we've been able to do some pretty neat things with the job CI that would have been a real pain to do with the UI. Things like moving a bunch of jobs between clusters all at once, or having it restart all the jobs when we change a shared component. And it was an ideal place for us to enroll the newly created jobs into our metrics platform so we get monitoring and alarms on these streams by default. The only caveat is that writing stacks JSON is pretty tedious, so we wrapped a CLI utility to generate them with a questionnaire. For the last thing we'll discuss, I want to take a step back from the detections and focus on some of the problems we've had in the triage space. If you look at the alert trends over time, you'll find that most of the events day to day aren't completely novel. It's very likely that something, maybe not the exact thing, but something similar already happened in the past and was already triaged and investigated or closed out. Particularly for analyst teams that operate 24/7 across multiple shifts, it's really difficult for any one person to remember all of this historical context. And it results in this waste of resources cyclically reinvestigating the same thing over and over again. The solution to this problem is research. If people read through all of the various tickets, wikis, and investigation notebooks, we curtail a lot of the wasted cycles. But these data sets exist in many different places, each with their own search syntax and interface, and it's unreasonable to expect analysts to have either read every document ever written or do these searches during alert triage when time is at a real premium. Because the data exists in disparate places, we can't effectively mine it for insights. Over the course of many years, we could handle multiple incidents that are seemingly unrelated, but actually share some common feature that's too obscure for any human to see. Mapping the relationships between alerts or incidents requires not just intimate familiarity with what's happened before, but also that the connection between them be so glaringly obvious that someone happens to notice it. So we built a solution to these problems we call doc search. To start, we centralized and normalized all of the incident related data. The text payloads of email correspondence, tickets, investigations, and wikis are all dumped into a Delta table, on top of which we built a document recommendation mechanism. Having a single place to search through all this knowledge was transformative on its own, but more importantly, it provided us with the means to programmatically leverage all the things we've ever learned to better inform what we do in the future. So, what does this look like from an analyst perspective? We have code that runs in all of the investigation template notebooks that'll take the alert payload and suggest potentially related documents in a pretty display HTML table. It includes some pretty useful features like the verdicts and analyst comments on the past alerts, and a matching term list where the document and the alert intersect, and clickable links into the system that it originally appeared in. For email correspondence, and this is pretty neat, when you click the link, it'll open up mail.app and macOS to the specific thread uh, where you can do some further reading. So let's take a bird's eye view of how this works. We'll go into more detail about each one of these steps here in a little bit. The template notebook will tokenize and extract specific entity types from the alert payload. It runs those entities through an enrichment routine to ensure that every possible representation is covered before looking for occurrences in all these documents. Since we're searching through unstructured blobs of text and the Spark SQL like and contains operation get pretty expensive, we use a more optimal concurrent string search algorithm called Aho-Corsic that prevents performance degradation as the term count increases. Depending on the input terms, there could be a ton of tangentially related documents we don't really care about. So the hits are run through a scoring algorithm to compute their relevance, and only the most useful results are going to be given to the analyst. To understand why we need to bother with entity tokenization, let's take a look at the structure of a typical alert. They're a set of key value pairs, and for the purposes of finding related documents, not all of them are created equal. Some of these strings, like dates or HTTP methods or ports, are going to be found across thousands of different documents, and almost all of them aren't going to be related to each other. There are also some in here that are too selective, like a timestamp, that would only appear in this specific alert and nowhere else. But there are a subset of tokens that describe different aspects of an entity and the machine or accounts that are involved in the alert. And these are the ones that are valuable for correlation. So we use a suite of regex expressions to extract the common entity types we care about. But that's not enough on its own. If you think about a physical machine like someone's MacBook Pro, there are many different identifiers that could describe it. It has a serial number, some MAC addresses, a host name, and potentially many different IP addresses over time if the system uses dynamic addressing like DHCP. Some documents might contain one or a couple of these, but never all of them all in one place. So you'll have documents all kind of referring to the same machine, but each one uses a different attribute to describe them, which makes tying them together pretty difficult. To address this, we've run the extracted entities through multiple enrichments, making sure that we're searching for the superset of those identifiers, and it'll find all the related documents regardless of which piece they contain. After entity extraction and the enrichment and searching on the documents, the results are fed into a suggestion algorithm that'll compute a term-wise relevance score. For each matching entity, we'll look at the number of documents it appears in over how long a period of time and its distribution across the different types of documents. The terms are ordered by an average rank percentile of those features such that the less common a term is across documents, the more valuable it'll be as an indicator of relevance between them. Documents containing this subset of valuable terms are going to be presented in order of how many they contain, with documents that have multiple hits going to the top of the list. And with that, that's all the content I have, so we'll open the floor to Q&A.